There we are. All right. Let's see. So today we're going to finish up with 3.1, and we're going to talk about more kind of application problems with exponential growth and decay. And then if we have time, we will also get to kind of a basic intro to logarithmic functions. If we don't have time, then we won't get there, and that's okay. So here we go. Oops, that's geometry's slide. I meant to click on this. Okay. So today we'll call this more like 3.1 part 2. And we'll have applications of exponential growth and decay. Okay, thanks for letting me know. I will post the video as soon as I can of class so that she can still get the stuff. Oops, and you guys can't see that. All right, 3.1 part 2, applications of exponential growth and decay. Okay, so when we talk about exponential growth and exponential decay, there's several, like with word problems and things like that, there's several different models that we tend to use. So the first one's going to be just like the basic exponential growth and decay model. Okay, basic exponential growth and decay. So the standard equation for this is n equals n naught, so n sub 0 is n naught, times 1 plus r to the t. Okay. So n naught is your initial amount. R is your rate of growth or decay. T is time. And n is your ending amount, or your final amount. At some time t. Okay, so that's your basic exponential growth and decay equation. And so we're going to do an example that involves this. So a lot of times our examples with growth and decay are going to be things like cells multiplying or money-related problems. Or you might have heard, like, of problems where you've got things that are breeding, like rabbits or bunnies, or rabbits or bunnies, those are the same thing, or guppy fish or something like that, where the amount of them grows exponentially over time because you start with 2 bunnies and then those 2 bunnies make more bunnies, and which makes more and more and more bunnies. So it grows at an exponential rate. Or you'll hear things like with cells that reproduce at an exponential rate. They divide and continue to make more and more cells. Or you might see things like, like radioactive things decaying and things like that, and so becoming less and less radioactive over time. So those are some examples of things that can grow and decay exponentially. So for our example, we're going to say there's an initial population of cells. And we're going to say that initial population is 100 cells. and they reproduce at a rate of 25% per week. So we want to find the amount after 6 weeks. Okay, so oftentimes this is the sort of problem that you would start looking at and kind of just reasoning your way into and around. Just kind of tossing some stuff into a calculator and trying to calculate, after 6 weeks what happens. But we can also use this exponential model here, and that's probably going to be the easiest way to get an answer that we know is accurate without having to kind of derive it and think our way around it each time. So the first thing we want to do is kind of identify these elements in our problem. So 100, it says the initial population of cells was 100, so that's going to be our N naught. That's our initial amount. And we know they reproduce at a rate of 25% per week, so that's going to be R. And 25%, we usually want to express it then as a decimal. So remember, 25% as a decimal would be 0.25. And then the amount after 6 weeks, that's going to be time. So once we've identified those three things, we're basically plugging them into this and figuring out what the ending amount is. So here we go. We have, instead of N equals N naught times 1 plus R to the T, we plug it in and get 100 times 1 plus 0.25 to the 6. So then we would just multiply these things, toss it into a calculator, and make sure you use your parentheses and everything correctly so that we end up with not just like 0.25 by itself to the 6th or anything like that. And when we plug that into a calculator, we should get approximately 381.47 cells. But since you can't have a portion of a cell, oftentimes you'll be dealing with things here that come in discrete values like cells or bunny rabbits or polar bears or whatever. So you want to round to the nearest whole number. So in this case, we would say our answer is 381 cells. Okay. So we're basically just identifying the elements in our problem that go into these locations here. So that's basic exponential growth and decay. Okay, so there's our first model. Any questions with this? Any numbers we're not sure where they came from? Steps we're not sure how they work? Okay, if at any point you do, feel free to unmute yourself and say something about it. The second model that we are going to work with, so I'm going to kind of block that one off. The second model is continuous exponential growth and decay. So something like a lot of money problems involve continuous exponential growth and decay, like interest and stuff like that. So continuous growth and decay comes with its own equation. It's very similar to the one above. It goes n equals, we still have n and n naught, but instead of 1 plus the rate to the t, it's going to be e to the kt, the number e. So this is where we start working with things with the e to the x type functions. So we have e to the kt. So kind of breaking out what we have here. Again, n naught is your initial amount. E is a constant. K is the rate of growth or decay. And T is time. And then N is your final amount. At time T. So we still break down those things pretty much the same way. The only difference here, instead of having 1 plus R, we have E. And then the rate is called K. Okay, so for example, the bank lets you invest $1,000 at 5% interest. Compounded continuously. How much money do you have in 10 years? Okay. I will slow down with the writing and let you all catch up. Okay. So just like with the last one, we start identifying things that are going to end up in our equation. For example, this would be our initial amount, the N naught value. 5% interest, that's going to be K. And we would write it as 0.05, since 5% as a decimal is 0.05. Compounded continuously is what tells us that we're going to be using this model at all. So if it's not compounded continuously, you wouldn't want to use this model in the first place. So this is only the case if it's compounded continuously. Okay, and then how much money do you have in 10 years? 10 years would be the time. Okay. So here we go. We have N equals N naught e to the kt. And we're plugging things in. So N naught is 1,000, e to the 0.05t, and then t was 10 years, so 0.5 times 10. So that is equal to $1,648.72. With problems like this, I would round to the nearest cent, since they likely will have, you know, a lot more numbers after it. But, you know, we don't deal with things in denominations less than a cent. But yeah, so that's how we do those ones. We kind of just pull the numbers out of the equation, or out of the word problem, and plug them into the equation. Any questions with that one? Okay. So the other kind of problem that we will see is something similar to this, but it's not compounded continuously. Instead, it might be compounded weekly or monthly or daily or something like that instead. So that'll be using a compound interest model. Do you need a constant in the E position? E is a constant. So E is actually a number. If you go to a calculator or to Desmos, it'll recognize it as a number. So remember when we were doing things like e to the x? That's that E value that we were talking about. It's the same number. It's approximately 2.72 if you were running to 2 decimal places, but it's irrational, so it continues on forever. It's kind of like pi. It's one of those values like pi or golden ratio or tau, or there's different things like that you'll recognize in math as you go along. E is one of those numbers. So E is a constant. So yeah, if you were to type in 1,000 times e to the 0.05 times 10, your calculator should recognize that value. Good question. And if you're using like just a regular calculator too, they should have an E button or an E to the X button. Okay. So yes, E is a constant all on its own. Yeah, so if you want to remind yourself, put in parentheses that it's approximately 2.718 ... You can. Because yeah, that's a new thing that we're working with here. Okay, so the last model that we're working with is a compound interest model. And so with compound interest, it might not be compounded continuously like this one. It could be compounded yearly or weekly or quarterly or whatever. So this one uses a little bit different in the way of letters in the initial equation. We'll see things like A equals P times 1 plus R over N to the NT. So this is the one that looks different. Or it looks different with, or it uses different letters, but it looks still very similar to the other equations. It looks the most similar probably to the first equation, because the only thing that's different about it is this N value that we're seeing here that you are dividing by and multiplying by on the time. So here we go for compound interest. I'm gonna kind of put down what these values are. So A is your final amount, or the amount at some time t. P is your initial amount. R is the rate. And then N is the number of times it's compounded in a year? Number of times compounded per year. So, for example, if you're compounded weekly, then n is 52, since there's 52 weeks in a year. Or if it was quarterly, then n would be 4, since there's 4 quarters in a year. Or if it's, let's see, compounded monthly, 12, because 12 months in a year, that sort of thing. And so for a lot of these problems, you'll see the same kind of financial type of problem. So for our example, we're going to use the same information as that one, but compounded quarterly. Same as that one, but compounded quarterly. Okay, so for this one, we're still dealing with A equals P times 1 plus R over N to the NT. And our initial amount, that N naught value, the $1,000, is now P. The rate, which was K up above, was that 0.05. That's now our R value, so 0.05. N, since we're doing it quarterly, N would be 4, since there's 4 quarters in a year. And then it's to the 4 times time, so 4 times 10 years. Okay, so with compounded quarterly, if I stick this into a calculator, if I go 1,000 times parentheses 1 plus 0.05 over 4, parentheses to the 4 times 10, or to the 40, we would get $1,643.62. So would you rather have it compounded continuously or quarterly? What do you think? Which one's better? Yeah, I agree, Sean. Continuously. Because you make quite a bit more money, right? Or not quite a bit, I guess, in this model. I mean, you're only investing $1,000 at 5%. But yeah, you still end up making about $5 more over 10 years. And we want more money, not less money. So yes, compounding continuously is a better deal for you. Okay. Any questions at this point? Or are we ready to try one? Okay, let's try one. And let's see, which one do we want to do? Oh, let's do a population one. Oops. Sorry, guys. There you go. Okay. I'm going to move this. And get some more paper going. Actually, let's just do the one that's on your homework, 3 and 4. Where'd it go? Okay. In the year 2000, the number of people in the United States was 281,421,906. So I'm just going to start writing down this information. Initial population was 281,421,906 in the year 2000. And it grows at 0.88% annually. And we want to know, we want a function that models the annual growth in the United States. And then we want to predict the population in 2020 and 2030. And the lights went off. Come on. There we go. Okay. So for this one, usually when you're dealing with populations and things like that, you're going to be dealing with the basic exponential growth and decay model. So that first model. So using that first model, the n equals n naught times 1 plus r to the t. And this information with your initial population grows at 0.88% annually. Go ahead and try writing a function that models the growth. So leave t as a variable and fill in the other parts. Also, if I were to leave, if I were to leave this one using, or as a function, I would have n of t equals 100 times 1 plus 0.25 to the t. So this is the sort of thing that we are looking for if we're just writing a function. Okay. So go ahead and try writing the function with this information. When you think you've got one, type Velociraptor in the chat. All right, Timo's already got one. Starting with n of t, you're on the right track. If this is your n naught, and your rate. So starting with our n naught, Then we just need to fill in what goes there, the rate. And if the rate is 0.88% as a decimal, that's going to be 0.0088. So this should be our function modeling growth in years since the year 2000. Okay. Any numbers on this, we're not sure where they came from. Any steps, we're not sure how they happen. Okay. So if I was going to predict the amount of people in 2020 and in 2030, I need to use the 20 and the 30. I wouldn't want to plug in 2020 for time or 2030 for time, because this function modeling growth is growth in years since 2000. So if it's 2020, it has been 20 years since 2000. If it's 2030, it's been 30 years since the year 2000. So for this one, we would be plugging in 20 and then plugging in 30. So go ahead and do that for time. Plug in 20 and plug in 30. If you want to type this into Desmos with the n of t thing so that you can type n of 20 and n of 30, feel free to do that. But give it a try. So I'll go over and do it as well. We had So if you do it like that, then you can just type in n of 20. Or if you want to, you can always plug in 20 for t and then plug in 30 for t. Either way is fine. So in 2020, we should have about, let's see, 335,319,933 people. 0.5, so we'll say 934 people. And then for after 30 years, we'd have 366,024,459 people approximately. Okay, so that's one type of problem that we could see. The other type is going to be more of a financial problem. So we'll do number 4 as well. It's going to be compounded monthly is what it said. So let's see, that problem is we are going to have a savings account with $1,000 to start. With an interest rate of 4%, compounded monthly. And we want to know how much money is in there after 5 years. Okay. So my first question for you guys, are we using the continuous exponential growth or the compound interest model? Continuous or compound? What do we think for this one? We awake today? Yes, there we go. Compound, yes. Because we don't see anything that says it's being compounded continuously. It's being compounded monthly. And so if we're doing compound interest compounded monthly, what's n going to be? If it's compounded monthly, what's n going to be? Exactly, it's going to be 12 because there are 12 months in a year. So go ahead and use the compound interest model. Try to show that along with it. Compound interest model. And figure out how much money is left after 5 years. When you're finished, type done in the chat. All right, Gabby's already done. And Timo is done. Nice. All right, if that is what you did, you went 1,000 times 1 plus 0.04 over 12 times 12 to the 5th. You're on the right track. And when we do that, we should get approximately $1,221 even. Okay. So there we go. Those are all of our models. Those are all of the different ways that you can do those those problems. Let's see. I think we will call it there with new information for today. So it is just going to be about exponential growth and decay today. And our homework assignment has just been posted. So if you feel ready to roll on the homework assignment, you're free to go and get started on it. It's 2 IXL sections today. If you would like to see more examples, you're free to stick around and we'll do more examples. And have a wonderful weekend.